So good afternoon, March the 2nd, 2015. This is MATB110 in section 1, calculus 1. Today is the first day of class after the Chinese New Year's holiday. So let's get started. Day number 13. Well, welcome back. You must have gone through a very happy Chinese New Year. 恭喜發財. Alright, so this particular week we have a quiz. Okay, that is quiz number 5. So you're going to get ready for this quiz, which is going to be, it's quiz number 4, I'm sorry, which is going to be tested on 3.6, 3.7, and 3.8, all right? So that is, I'm sorry, it's March 11, no, not this week, next week, okay? So I got a little bit confused myself. But the homework is due this week, Wednesday, all right? So, but there's one thing I have done, and I would like to remind you to make sure you do not make this very careless mistake. Now, in order to validate your score you obtain for your quiz, for your homework, you must submit the scanned copy of your quiz and also of your homework in the Moodle environment. Because the department requires what we call a scanned manuscript of all the work done by students before the score could be validated, and I have to follow the rules. So that means if you have not submitted the scanned copy of your graded homework or your graded quiz, make sure you submit them, okay? Nay is not a problem, but if you do not submit them, it's going to be a problem, okay? So make sure you understand that. All right, so this is very important. I will send to you individually a message of your record of submissions and your score there too, but make sure you complete the submissions of the scanned copy of those graded homework and quizzes as soon as this week, okay? So now allow me to inform you one more time. Well, this is the message released at the end of week number 6. That means in the week ending February 14, and you have the 5th assignment due this Wednesday, and you have the 4th quiz, which is going to be conducted on March 11. Okay, that means next week, somewhat like this. And then your next journal will be due actually this Wednesday, okay? And this journal is going to cover on those sections, okay? So the best you could, make sure that you try to provide some notes based on these sections, all right? So you could write your notes, but make sure you provide a scanned copy of the notes in legible writing format, all right? So read some of the instructions there, understand the expectations. Normally, notes taking will give you a very good chance to review the material, all right? So today, what we're going to do is we would like to go back to your chapter 3, how to understand the very last sections of the chapter 3, which is successive approximations and Newton's method. And we will bring back Professor Hubert Strand to help us understand that. So let's get started with that.
The second application is to solve an equation. We're often, and I use a different letter, capital F, just because it's a different function and there will be different examples for this one. So I'll just chose capital F to keep them separate. This is the problem of solving an equation. And Newton had an idea, and it's survived all these centuries, and it's still the good way. Okay, what's this based on? Both of them. That's the point. They're both based on the same idea, is that suppose at a point which is near the x you want, or near the solution for this problem, at some point, let me call it A, suppose we know the slope, the derivative, at that point. So I'm using f prime for the derivative. At that point, well, we know what the definition is, but I'm also supposing that we've got that number. And now I want to use this knowledge of the slope at that nearby point A to come close to the solution, the f of x or the x there. Okay, well, you remember this is delta f divided by delta x. You recognize that before we take the limit, this is two nearby points, delta x apart. Their values, the values of f at those points, it's the change in f divided by the change in x. That's what the derivative is as one point approaches the point A where we know the slope. Okay, here's the idea. I'm just going to erase that stuff. Well, now I won't have an equal sign anymore. I'll have an approximately equal. So the slope is, this is delta f over delta x, is not the same as df dx, which is this. But if x is close to a, this will normally be close to the correct slope, the instant slope at the point. I'm just going to use this approximation to find a good approximation for f of x. So in this application on the left, I know the x, and I want to find what is f at that point. So I look at this, I multiply up by x minus a, I move the f of a to the other side, and what do I have? I've got a great, I still have an approximation sign. So when I move the f of a to the other side, there it is. And then the other part is x minus a times f prime at a. That's my formula. Let me just talk about that formula for a minute and then give examples. What that says is that if I want to find the value of f at a nearby point, a good thing to do is use this linear approximation. I use the word linear because the graph of that is a line. I'm following a straight line instead of following the curved graph. That's the message of today's lecture. Follow the line. So it's a line, it starts out at the correct point at x equal a, it has the correct slope, f prime of a, and if I don't go too far, that line won't be too far from the curve. Good, you'll see it now in examples. Let me get the corresponding idea here. Now I have to remember to use capital F, so let me create the formula that helps to solve, approximately solve, this equation. What's the difference? Now, x is what I'm looking for. X is what I'm looking for, and f of x is what I know. I know it's to be 0. So, I'm going to use this with capital F. I know f of x should be 0, and x is the unknown. So, can I just move that equation around again to get an equation? I'll bring the x minus a up as I did before. And I have to use an approximation sign as always. The f of x is 0. So I have minus f of a. And then I'm dividing by f prime of a. There you have it. That is Newton's insight. Newton and then somebody named Raphson helped out, made it work for general functions. And once again, I forgot, I should be using capital F there. Because in the right side of the board, I'm calling the function capital F. This is the little movement of x away from A, which will bring us closer to the answer. You'll see this formula work in a picture. So I'm ready for an example, starting with approximation. So here's my problem. Here's my example. Find the square root of, so my problem is going to be find the square root or approximate square root of 9. I'm going to shift away from 9 a little bit, 9.06. Okay, how does that fit this example? My function is the square root function, x to the 1/2. Its derivative, f prime, I know the derivative of that is 1/2 x to 1 lower power minus a half. So that's 1 over 2 square root of x. Good. I know my function, I know its derivative. Now I pick a point A, which is close and easy. So close, I'm looking for a point A, which is near 9.06 and has a nice square root. Well, 9. So I'll choose A to be 9. The correct value, f at the point A, is the square root of 9. 3, that's the point. We can evaluate the function easily at 9. And f prime at A is 1 over 2 square root of A, 9, square root of 9. So what do I have for that? That's the easy number, 3, that's 1/6. In other words, I know what's happening at x equal 9. And that's the particular point I'm calling A, and I'm working from there. Then what does my approximation say? It says that f at this nearby point, so x is 9.06. This is the x where I want to know the square root. So this is saying the square root of 9.06, that's my f of x, is approximately f at A, that's the square root of 9, that's the 3. So far reasonable. That's the approximation I started with, just using the 9. But now I'm improving it by the difference between x minus 3. Well, what is x? X, I'm plugging in x is 9.06. That's where I really want the square root. That's my x. Minus A, which is the 9, times f prime, which we figured out as 1/6. That's the linear approximation following this line to this number, which is what? 3 plus, that's 0.06 divided by 6, that's 3, what do I have there? This difference is 0.06, divide by 6, and it's 0.01. That's the approximation, closer than 3, that comes from following the line. Let me draw a graph to show you what I mean by following the line. Here's my square root function. The square root looks something like that. And here's the point, x equal 9, where I know that the height is 3. What else do I know? Here's 9.06, a little further over, and I'm looking for that point. I'm looking for the square root of 9.06. So this was 9 here, and this was 9.06. And how am I getting close to that point? Well, I'm not going to follow the curve to do square root of 9.06 exactly, any more than your calculator or computer does. I'm going to follow this line. So that line is the tangent line. It's the line that goes through the right thing at A with the right slope. So you can see that by following the line, so that gave me the 3, and then here's the little, you see what I'm missing by a very small amount, practically too small to see. I'm picking the point on the line, and that was this across, this delta x was the 0.06, the little tiny bit here is the 0.06, and this delta f is the little piece that I added on the 0.001. Because, how did that come from? It came from the fact that the correct slope is 1/6. If I go over 0.06, I should go up 0.01. So you see what I'm doing? I'm taking that point as my close approximation to the square root, closer than 3, to the square root of 9.06. Okay, that's a first example. I'll give a second one. But first, I'd like to give an example that's like this one of Newton's method. May I change now to Newton's method? So I want to create an equation, and actually I want it to solve the same problem. So I'm going to take my function to be x squared minus 9.06, and I'll set that to 0. I'm just keeping my two examples close, because the answer is, I'm still, in both problems, I'm looking for the square root of 9.06. Okay, so, of course, that's the solution to this equation, the square root of 9.06. Okay, again, I pick a point A close to the solution, and again, I'm going to take A to be 3. Okay. So 3 is close to the correct solution. Correct x is, this is the correct x is the square root of 9.06, but I'm starting close to it. Okay, at that point, I figure out f of a. Newton wants to know f of a, the value, and Newton also wants to know the slope. So the value at a is 3 squared is 9, is 9 minus 9.06 is minus 0.06. F prime of a is, what's the derivative of f? Capital F? Well, the derivative is certainly 2x, and at the point A, it's 6. This is the 2x, 2a. This is the 2a, because I'm evaluating the slope at the point A. Actually, if you want a picture, it's quite interesting to see the picture. Let me graph this f of x now. What does my function f of x look like? X squared, that's a parabola going up. It starts below here, it starts somewhere down here, and it curves up like so. And actually, so this is the point I want. This is there is the square root of 9.06. I graphed the function x squared minus 9.06. That's the point I'd like to find. I'm not expecting to find it exactly. What I do is I have a nearby point 3. At 3, I do know the exact value, and I know the slope. Ha! Even my bad art is telling me what's going to happen. At 3, this is, let me write that 3 better. A equals 3. This is where I know what's happening. I know the value of f. It's actually pretty small, but it's negative. I know the value of the slope. So this is like I've blown up this picture here. Yeah, this f is the negative 0.06. Is the value of f. The slope is 6. And what's the x? What is my improved guess at the solution? My improved guess, I don't follow that curve, because that would be perfect, but curves are hard to follow. I'll follow the straight line, and that's my next x, my better x. You see, that's a lot better. Oh, let me do the numbers here, and you'll see that it's a lot better. What is the x that Newton's method gives us? I'm using Newton's formula here. So Newton's formula says that x minus the a is 3, and Newton's formula is going to take equal to get an approximate x. Minus f of a, so what's minus f of a? That'll be plus 0.06 divided by f prime of a, the slope, which was 6. What do I get? I get 0.01. Actually, the two examples, of course, are parallel in a way. The graph of that square root function kind of got just flipped to this graph of the x squared function. The square root function and the x squared function are just sort of inverses to each other. Their graphs flip, and so now the slope is 6 instead of 1/6. And if I go, you see that distance, this is the x minus a distance that has to be 0.01. That's what I conclude. I go across 1 if I'm going up, down by 6, because the slope is 6. Okay, good. Now, how close am I? Well, I can't resist asking. Suppose I multiply 3.01 by 3.01. Am I close to the 9.06 that was my whole goal? And how close? Of course, I'm not going to be exact. If I do that multiplication, I get 301, 903, combined, I get 9, and the decimal, put it in there, 0601. So, by that method or by that method, I ended up with 3.01 as much closer to the square root of 9.06. You see, when I squared 3.01, it slightly overshot. It slightly overshot the 9.06. This little error there. This is the overshoot error. And when I square it, it's way out in the 10,000th place, the 4th decimal place. Okay. So those were two parallel examples. May I go back to the linear approximation, because I think another example's appropriate there. And then I'll come back and give another Newton example. So that's my plan here. 2 examples of each. Okay. So those examples were parallel. The next 2 examples will be a little different. Okay. So let me show you example 2. So linear approximation. Example 2. So I want, okay, I'm going to look for something that I don't know exactly. Let me take e to the 0.01. What's the value of e to the power of 0.01? Okay. So the function is e to the x. and I'm looking at x is 0.01. That's what I want. I am not going to get an exact number. I'm going to follow the tangent line. I'm going to get a close number. So where shall I start? I'll start with a number that's close to that, and where I do know the correct e. And the number close to that is I'll choose a to be 0. That's close to 0.01. Then f of a is e to the 0 power, so that's 1. Now for the straight line approximation, I also need the correct slope at a. Well, I do know the slope of this. F prime at 0, that's my a. F prime at 0 is my a. Well, I know the derivative of e to the x. That's one thing I like. It's e to the x. So at x equals 0, again I get a 1. E for the derivative, which is the same, I get e to the 0, I get also a 1. So now I know what's happening at a equals 0. I want to know approximately what's happening at the nearby point, 0.01. So what does e to the 0.01 is approximate, or yeah, e to the 0.01, e to the x. This is e to the x. That's my function. And I'm only going to get it approximately, is the value at this known point, the value of, at the known point 0, the exact exponential is 1, plus x minus a times the slope, the correct slope at this not quite perfect point, 0, and the correct slope is 1. And of course a was 0. So you see I'm using all the facts at a to get an approximate fact at x. And what have I got here? I've just got 1 plus x. You know, in a way that's perfect, because it shows what the linear approximation is doing. You remember the series for e to the x? My correct function is e to the x. My approximate function is 1 plus x. What's the connection? You remember that e to the x, the series for e to the x started out 1 plus x plus 1/2 x squared, 1/6 x cubed. Those are the guys, those are the higher order corrections that the straight following the line misses. Those are the parts where the function, the curve e to the x has left the line. But if I don't go too far, so 1 plus x is so this is 1.01. X is 0.01. That's my approximation. 1 plus x. That's the thing to notice. That linear approximations, and you could come back to that, the formula for any f and any a. Linear approximations are just like those power series, just like the e to the x equal 1 plus x plus 1/2 x squared plus so on, except we cut them off after just the constant term and the linear term. That's what this linear approximation is about. And you might say, what's the next term? And of course we know that the next term is 1/2 x squared. And you could ask, what's the next term in this? In the general case, actually, let me tell you, the next term, next would be, but we're not using it, would be the 1/2, it would be the x minus a squared, and it would be the second derivative at a. If we kept it, that's what we would keep. Okay, good. You saw the main point of linear approximation, stop at the linear term. Finally, I go back to an example of Newton's method. A second example of Newton's method. So I've been thinking, what should I do? Let me use Newton's method the way it's really used. The way you use Newton's method is you do this to come close to the solution, and then you do it again. You do it again starting at 3.01. So I plan to do just the same thing for the next step of Newton's method, except the A, so f of x is still, I'm still aiming to solve this same equation, but I'm going to get closer than 3.01. I got closer than 3 to 3.01, now I'm going to restart there. A is now going to be 3.01. I need to compute f of A for Newton's method, so I have to do 3.01 squared and take away that to see how wrong I am. We did 3.01 squared actually right there. So if I take away the 9.06, the f of A is, well, that was the whole point, that it was pretty darn close. But nothing compared to the closeness we're going to get at the second term. Okay, and what's f prime of A? Take the derivative 2x. At the point A, it's 2a. And A is now 3.01, so the slope is 6.02. You see what I'm doing. I'm just moving over to this point, which was now, that has become now the A in the second try, A in the second cycle of Newton's method. This is how Newton's method really is used. And now let's find the new x, the highly improved x, the better than 3.01. So Newton's method says x, the new x, minus A. I'm just using Newton's formula. X minus the A is supposed to be minus the f of A, so that's 0.0001 divided by f prime of A, 6.02. This is the delta x, you could say. This is the little correction. It's negative. It means that we need to pull back a little. And you see that. We slightly overshot by following the tangent line. The curve went up a little, across zero, a little before the tangent line. This is extremely close to, so now this gives me the new x. Right here, 3.01 minus this tiny little bit. And so that's what the calculator will do. I hope you'll do it on the calculator. Just make the calculator take that quantity, then make it square it. So this new x, let's then just go through this. Find the new x, square it, subtract 9.06. Let's see how close it is. I believe that the error, I don't know what it is. That's more than I can do in my head, squaring that 3.01 minus this little tiny bit. But I am confident that the error, the x new squared, so this is the formula for x new, the second cycle of Newton's method. I think that minus the 9.06, I don't know how, can I just put a bunch of zeros? Somebody will want me to put in a 1 here, so I'll put in a 1. I've got this way out there. So Newton's method is really a terrific success. Follow the line, then follow the next tangent line, then follow the next one, and you home in very, very quickly on the exact answer. You get more and more decimal places correct. Okay, that's two uses of calculus coming from the same idea. The same idea, delta f over delta x. In one case, it was f that we didn't know. In this case, it was x that we didn't know. In both cases, that formula gives a terrific and a terrifically simple and close approximation to the exact answer. Good. Thank you very much.
Well,
This has been a production of MIT OpenCourseWare and Gilbert Strang. Funding for this video
well, if you understand the kind of explanations here, you should be able to apply the same context to understand example 1 to 4 onto pages 206 through 209. And that is the very last sections in your textbook for chapter 3. Okay? So I would like to do a backward revisions now. Now take a look at sections 3.9 now. What section 3.9 all about? It's about implicit differentiations in related rates. We handled it already. Now let's take a look at 3.8, all right? Because this is something in your coming quiz. The 3.8, it's about the exponentials and logarithmic functions. I would like to walk you through one more revisions by Dr. Gilbert Strang, because these are very useful explanations here. Okay, this is growth rate and log graph. Another 30 minutes review. Make sure you make the best use of the following. Let's go for it.
Okay, hi. I thought I'd give a short lecture about how logarithms are actually used. So, a little bit practical. And also, it naturally comes in, how quickly do functions grow? Which functions grow faster than others? And I made a list of a bunch of functions that we see all the time. Linear growth, just the function goes up along a straight line, proportional to x. Linear could have been a c times x, still linear. Here, that's called polynomial growth, like some power of x. Here's faster growth. We introduced e to the x, and I'll take this chance to bring in 2 to the x and 10 to the x. Especially 10 to the x, because that'll lead us to logarithms to base 10, and those are handy in practice. And then here are some, so that's exponential growth, and here are some that grow faster still. X factorial, n factorial grows really fast, and n to the n, for x to the x, is a function that grows still faster. And of course, we could cook up a function that grew faster than that. X to the x to the x power would really just take off. And we could find functions that grow more slowly. But let's just take these, and let x be 1,000, just to have a kind of realistic idea of how these compare when x is 1,000. Okay, so I'm skipping the c, so x will be 1,000. 10 cubed. Let me just write it as 10 cubed. Because these are big numbers, so x is going to be 1,000. And because these are big numbers, I'm going to write them as powers of 10. Okay. So how about 1,000 squared? 10 cubed squared will be 10 to the 6th. 1,000 cubed, we're up to 10 to the 9th. And onwards. Like this is where the economists are working. The national debt is in this range. Okay, now, fortunately, it's not in this range. 2 to the 1,000th power. And if I want to be able to compare it, I'll write that approximately as 10 to, well, if it's 2 to the 1,000th power, it'll be 10 to a smaller power, and 300 is pretty close for 2 to the 1,000th. Then e to the 1,000th, that's going to be bigger than 2. E's 2.5. 7, etc. This is more like 10 to the, I think this is right, about 434 maybe. And 10 to the thousandth, well, I can write that right in, 10 to the thousandth. When x is 1,000. Okay. So that's one that's exactly right. And also I could write in 1,000 to the thousandth power. What power of 10 will this be? 10 to the what? 1,000 to the thousandth power, I think, is 10 to the 3,000. Why do I think that? Because 1,000 itself is 10 times 10 times 10. Three of them, right? And then we do that 1,000 times, so we have a string of 3,000 tens multiplying each other, and that's what 10 to the 3,000th is. And you might wonder about 1,000 factorial. Let me make a rough estimate. A big number factorial is order of magnitude is something like, it doesn't grow as fast as this because this is x times x minus 1 times x minus 2. 1,000 times 999 times 998. So we're not repeating 1,000 every time. And the difference, it turns out that this number divided by this number, x to the x over e to the x, is the right general picture for factorial. So that would be, if I divide 10 to the 3,000th by 10 to this power, what do I do in a division? I do a subtraction of exponents, because I have that many fewer tens multiplying each other. So I think it'd be 3,000, but I don't want the full 3,000, because I take away e to the 1,000th, 434 of them, so that's about 200, 2,566 is close enough, anyway. Okay, giant numbers, and of course you saw that I didn't write it out with 1 and 3,000 or whatever zeros. Hopeless. Okay. In other words, it's the exponent that gives me something I can really work with, and the exponent is the logarithm. That's what logarithms are. They're the exponent. And when they're the exponent with a 10, I call 10 the base, and I'm speaking about logarithms to the base 10. Can I just copy those numbers again? And then I want to write their logarithms, because it's the logarithms that kind of remain reasonable looking numbers, but tell you very nicely what's growing fast. So let me write out again 10 cubed, 10 sixths, 10 to the 9th. These polynomial growth starting with the first power. Then I'll write down 10 to the 300th approximately, 10 to the 434 I think is about right, and then 10 to the 1,000. And then I had 10 to the 2,566 as something roughly 1,000 factorial, and then 10 to the 3,000. Okay, I just copied those numbers again. And now I plan to take their logarithms. I can see what's happening with logarithms. The logarithm of 10 to the 9th is, if the base is 10, the logarithm of 10 to the 9th is the 9. This has logarithm 6. This has logarithm 3. So you see, well, if we took the logarithm of the national debt, it wouldn't look too serious. We'd just be up around 9 moving toward 10. But what I'm using it for here is to get some reasonable way to see 300. Of course, that's big. For a logarithm, that's a very big number. 434, 1,000, these are climbing up, 2,566, and 3,000. Okay. So these are the logs. Just to repeat, if I wanted this growth, this list of functions by how fast they grow, where would log x appear in my list of functions? It would be way at the left end, slower than x, much slower than x. Log x grows very slowly, as we see here. And then if you wanted one that really grew slowly, it would be log of log x. That creeps along, eventually gets to, passes any number, but x has to be enormous. Okay, and one more little comment before I begin to use some things graphically, because that's the other part of this talk is the graphs, using logarithms in graphs. A little point, you might ask, what about functions that decay? What would be the corresponding functions here that decay? Let me write them here. Decay. By that I mean headed for 0 instead of headed for infinity. Well, 1 over x. 1 over x squared. 1 over x cubed. X cubed. Those functions go to 0. Faster and faster. Now, what about these? The next list would be 1 over, I'm dividing them, 1 over 2 to the x. 1 over e to the x. Can I write that in a better way? E to the minus x. 1 over 10 to the x. Those are going to 0 like crazy. And of course, if I keep going, even worse. So like x to the minus x power would be really small. Okay, so my point is just that we have a scale here that not only gives us a handle of how to deal with things that are going very fast, but also things that are going to 0 very fast. The other, the negative logarithms, the logarithms of these things would be minus 3, minus 6, minus 9, and so on, if I divide by 1. Good. All right, so that suggests the idea. Now I want to introduce the idea of a log scale. So I'm just going to think of a usual straight line on which we usually mark out 0, 1, 2, 3, minus 1, minus 2. But on this log scale, the center point, the 0, is, I'm really graphing the logarithm of x instead of x. That's the point. That in this log scale, what I'm picturing along here will be, this number will be 10 to the 0 power, which is 1. The next one will be 10. The next one will be 100. The next one will be 1,000. So you see, within this picture, on a graph that we could draw and look at on a printed page, we can get big numbers by going from the ordinary 1, 2, 3 scale to the log scale, which puts these points in this order. And let me put some of the other ones. Now, what point goes there? 1/10. Every time I go that far, I'm multiplying by 10. When I go this way, I'm dividing by 10. Up there, this is the number 1/10, which is the same as 10 to the minus 1 power, right? Here's 1/100th. Here's 1,000th, and so on. So this log scale is able to deal with very small numbers and very large numbers in a reasonable way. Okay, and everybody sees the point here. That really what it is the logarithms. So this is 0, this is 1, 2, 3, and so on. Minus 1, minus 2, minus 3. If I'm graphing really these are the logarithms of it. And I'm doing logs to base 10 again because that gives us nice numbers. Okay, by the way, what's that number? What's that number in halfway between there and there? It's not halfway between 1 and 10 in the ordinary sense, which is whatever, 5.5. No way. Halfway between here is, do you know what it'll be? It'll be square root of 10. 10 to the 1/2 power. The half is here. The log is a half, so the number is the square root of 10. That's about, 3, a little more than 3. And what would be here would be 10 to the minus 1/2, 1 over square root of 10. So you see that picture. Oh, I have another question before I use these scales. What if I like powers of 2 better? In many cases, we might prefer powers of 2. If I plotted the numbers, I'm looking at this log scale, and suppose I plot the numbers 1, 2, 4, 8, whatever, 16. What could you tell me about those? Well, I know where 1 is. It's right there. That's the 1. Well, 2 would be a little further over, then 4, then 8 would come before 10, and 16 would come after 10. I pointed there, but 16 would not come there. 16 would be a lot closer, I think, in here. What's the deal with 1, 2, 4, 8, 16 on this log scale? They would be equally spaced. They would be equally spaced. Of course, the spacing would be smaller than the 10 spacing. If I multiply, every time I multiply by 2, I go the same distance. After I've done it about 10 times, multiplied by 2 10 times, so that's 2 to the 10th power is close to 1,000. So 10 powers of 2 would bring me pretty near there. Anyway, and here's one more question. Where is 0? If my value, that I wanted to plot happened to be 0, where is it on this graph? It's not there. You can't plot 0 on a log scale. It's way down at the, it's at the minus infinity end of the graph. Infinity is up there at that end, and 0 is down here. Okay, good. So can we use that log scale? How do we use that log scale? Let me give you an idea for what use that log scale might be. Practical use. Suppose I know or have reason to believe that my function might be of the form y is something times x to the nth. I have some quantity y, the output, when the input is x. But I don't know that number a, so I've done an experiment, and I would like to know what is a, and especially what is n. That's the, I would like to know how the growth is progressing. And I'm just taking, simple growth log here. Okay, I would graph it. I get a bunch of points, I put them on a graph, and I look at the graph. Now, if I just graph these things, if I just graph that y, here's x and here's y, suppose I'm graphing, suppose n is 1.5. Suppose my growth rate, and this is very possible, is x to the 1.5. And a is some number, who knows, could even be 1. Suppose a was 1. So I would, or even, okay, suppose a was 1. So then I'm graphing y as x to the 1.5. What does that look like? Well, it looks like that. The problem is that if the real growth, the real good relation, see, I would have a few points that might be close to that curve. But if I'm looking at that curve, I frankly could not tell 1.5 from 1.6 growth rate. The truth is, I couldn't tell it from 2. I couldn't tell what the actual growth rate is from my graph, which has a little error, so I'm not too sure. And the point is, x to 1.5 and x.2 would all, if I sketched the graph, it would look like that. But go to the log scale. Go to a log graph. So I'm going to take logs of both sides and look and plot that. So I take the logs of both sides, so I take the log of my outputs, y, and now this is a product of that times that. What's the rule for logarithms? Add logarithms. So this would be log a plus log of x to the nth. But now what's the log of x to the nth? Beautiful again. This is x times x times x n times. At least if n is an integer. Think of it as x multiplied by itself n times. When I take the logarithm, I add n times. Log of x to the nth is n log x. Now that, let me graph that now in a log. This is now a log picture. So I'm graphing log y against log x, which was the whole point of my log scale, to think of doing this. Okay, and what kind of a curve will I see from this equation on this graph paper? A straight line. A straight line. That is some constant plus some slope. N will be the slope times the x. It's like capital Y is capital A plus n times capital X or something. But better for me to write log so we remember what it is. So on this paper, so if it was this particular, suppose I did the example x to the 1.5. Okay. So in this example, a is 1 and n is 1.5. So what will my points look like here? Now remember, I should really allow negative logarithms, because x could, this is the point, right? This is x equals 1 here. The log is 0, but the number is 1. Huh. Okay, so, yeah, so when the log is 0, you see, it's going to be a straight line. It's going to be a straight line, and actually when I took a to be 1, its logarithm will be 0. The line would go right through there. It would have a slope of 1.5. My points will be really close to a line. I measure out, if I go out a distance 1, then I go up a distance 1.5, right? Up 1.5. When I go across by 1 on the log picture, it could be down here. I mean, my numbers could be smaller or larger. A straight line, I can get out a ruler and estimate the slope far more accurately than I could here with a lot more software. Okay, so that's a important, very important instance in which we wonder what the rate of growth is, and the graph shows it to us. I'll just make a little point that I put some points here, like near a line, and that raises another graph question of very great importance. Suppose you have some experiments that put points close to a line, but not right on a line. You want to fit a line close to the line. You want to fit the best line to the experimental points. How do you fit a straight line? That's an important thing, and let me save that for a future chance, because I want to tell you about it. The standard way is what's called least squares. So least squares is a very important application, and the best line, it turns out, is a calculus problem. So, for the moment, let's pretend they're right on the line. Its slope, which we easily find, tells us this number. May I mention one other behavior? So, another possibility. If y is not growing polynomially, but suppose y is growing exponentially. I'll just put it here because it's not going to be a big deal. Y is some, I'll call it b, e to the cx. So that's a different type of growth. That's the big part of today's lecture, is to say this is a quite different growth. But it would be equally hard, or even harder, to find this growth rate c from an ordinary graph. The graph would take off even faster than this one. You couldn't see what's happening. The good idea is take logarithms. But what do we want to do? We'll take the logarithm of y, log y, as before, will be the log of b plus the log of e to the cx. Oh, maybe I should have made this 10 to the cx, just to make it all, instead of the e, I could use the 10, whatever. Because I've been talking about logarithms to the base 10, so let me use the powers of 10 here. What's the logarithm of 10 to the cx? When the base is 10, the logarithm is the exponent, c times x. So what am I seeing in this equation? That's an equation, when I've taken logarithms, my big numbers become reasonable, and also very small numbers become reasonable, and I get a straight line again. I get a straight line, but it's not in this log paper. The logarithm of y, the y-axis, the vertical axis, is still log scale. But you see it's ordinary x there now. So I don't use log x for this one. I just ordinary x. It's semi-log paper. Logarithm in the vertical direction, ordinary in the x direction. Okay. Good. Now, I just want to add one sort of example, because it's quite important and also quite practical. May I tell you about a particular, let me ask you the question, and see if you get an idea, because this is like basic to calculus. Let me talk about, this E will stand for error. Error, E, and what error am I talking about? I'm talking about the error as the difference between the derivative. I have some function, f of x, and there's its derivative, and I compare that with delta f over delta x. So what do I know? I know that as this is a function of delta x, I'm comparing the instant slope versus the average slope over a distance delta x. Now, so it's not zero, right? This one is a finite movement, delta x, produces a finite movement, delta f. As delta x goes to zero, that does approach this. So here's my question. My question is, this is approximately some constant times delta x to some power. And my question is, what is n? How close? What's a rough estimate of how near the delta f over delta x is to the actual derivative? Okay. So, I have to tell you what I meant by delta f over delta x. I meant what you also meant, f at x plus delta x minus f at x divided by delta x. In other words, that's the familiar delta f moving forward from x. I would call that a forward difference, a forward delta f, because I'm starting at x and I think of delta x as moving me a little bit forward. So I get the delta f, I divide by the delta x, and that's what this thing means. And do you know what n is? Let me connect it to my pictures stuff. If I tried to graph this, I'd have a graph. You know, here's my delta x and here's my e. This difference, as delta x goes to 0, it goes to 0. And, you know, if delta x is small, e is small. If delta x, if I divide delta x by 10, e divides by something. Yeah, I don't even know if you can see it on the camera. The graph has gone into a black hole or a chalk hole or a white hole or something. It's just completely invisible. I can't see the slope of this thing. But if I did it on log paper, I'd see it clearly. And the answer would be 1. The error, the difference between derivative and average slope goes like delta x to the first power. Okay, and we can see later where that 1 comes from, and we can see where that a is. That's all in Taylor series. But here's my practical point. There's a much better delta f than this one. A much better, a delta f over delta x, an average slope that's much more accurate and that in calculation I would always use. And the trouble with this one is, it's lopsided, it's one-sided. I only went forward. Or if delta x is negative, I'm only going backwards. And it turns out that the average of forward and backward is like center it. Center that difference. So let me tell you a centering difference. F at x plus delta x. So look a little forward, but take the difference from looking a little backward. That would be my change in f. But now what do I divide by to get a reasonable slope? Well, this is the change in f going from minus delta x to the left of the point, to delta x to the right of the point. The real movement there in the x-axis was a movement of 2 delta x's. So I would call this a centered difference. Can I write that word centered down? And if I use that, which is a lot smarter, if I'm practically wanting to get pictures, then what happened?
Unfortunately, the bandwidth has just stopped where we wanted 50 seconds more. But anyway, I think you got the idea. This is
So if this is now, instead of choosing this lopsided, simple, familiar, but not that great difference, if I go for this one, the answer is n changes to 2. N is 2 for this one. The accuracy is...
Okay, let me take attendance first. We thank you very much for this. If you look at sections 3.8 and some of the minor
way better.
exactly what it's talking about.
And the point about the log graphs is, if I plot those points on a graph, I would see that slope of 2 in the log.
Boy, the bandwidth is slow. It's okay. Let me just forget about attendance for this class. We need to go. This time is running out for this class. It's an important revision for you, for log, and also the linear approximation to it. Hope you're enjoying it, okay?
It would be, again,
Okay. Thank you. You can go because you have another class to come up. So that's it for today's MATB 110 Sections 1, Calculus 1 for day number 13. If you're this first day, stay tuned.